So again, when we get to the modeling phase and we are building and comparing and evaluating different machine learning models, there's a very important theorem that you should always remember, which is the no free lunch theorem. So this theorem tells us that there is no one single model that will work for all types of data sets and solve all problems. It just doesn't exist. So models can work to solve one particular problem that it has been trained and it learned to solve it. But if you move that model to a completely different setting, then there's higher chances that this model will not perform good or will not perform as good because that's not what it has been trained to do. So there is no model that can solve all problems that's universal and it can work with all different data sets. So here I want to discuss the main idea with machine learning models, which is the phase of model training. We're going to be using this word a lot, training the model or model training. So what does that mean? So model training is a process where our system learns to make predictions based by adjusting its own internal parameters. So a metaphor here or an example, you can think of a sculptor molding clay that with the ultimate objective of creating a statue. Okay. So the clay represents our raw data that we feed our model, and the sculptor's hands are here analogous to the training process. We are shaping our model, okay? We're shaping our statue. And so the training data that comes from our data set is very important for model development. So the model tries to understand the different patterns within the data, just like when the sculptor is trying to put together all the clay products and tries to touch it and understand the different materials and the characteristics of the clay. And then suppose we are making a predictive model for car insurance premiums. And so during the training phase, our model learns the relationship between, for instance, incurred losses and premium amounts. And so it tries to adjust its own internal parameters to capture these nuances or these relationships. So after the training stage, then we move to what we call the validation stage. And so validation data acts as the critical eye, which provides feedback to optimize our model. So it evaluates how well our model is performing during its refining phase. So we've trained a model and we are currently refining and fine-tuning its parameters. So we are adjusting the parameter for a more polished outcome. Okay. And then the final stage is the testing stage. So then test data will serve as the ultimate assessment, which will evaluate our model's real-world performance. Our completed model is now showcased to the world, and we use test data to see how well it performs in predicting, for instance, car insurance premiums, which this model has been created for. So we will try to see how well it will perform in predicting car insurance premiums for new unseen test cases that the model has never been trained on. And so since we have three stages, which is training, validation, and testing, this gives you an idea that we will have three different subsets of our data. And so we're going to create a subset for the training phase, which we call training data, and then out of the remaining data, we'll create a subset for the validation stage, which we call validation data. And lastly, the remaining goes to the testing data. So when it comes to how can we split it now between train, validate, and test subsets, so you can go anywhere between 90 to 60% for training, okay? And then the remaining goes for validation and testing. You can split it however you want. The common proportion is 80% for training, 10% for validation, and 10% for testing. Or you can go 70% for training, 20% for validation, and 10% for testing, or the other way around. So all these are acceptable proportions. It's up to you to define how you want to split your data, and also based on the size of your initial data sets, as we will see later when we come to the evaluation chapter. Now coming to describing one of the main challenges in machine learning techniques, which is the trade-off between underfitting and overfitting, and between specification and complexity. So let's start with defining what each one of these terms mean. So let's start with underfitting. So underfitting happens when a model is too simplistic to capture the underlying patterns in the data. So the problem is this model will fail to learn from the training data, which will lead to poor performance on both training and testing data. Okay. Now, the second term, which is overfitting. So overfitting happens when a model now is in the opposite now. The model is too complex. It's actually capturing noise in the training data as if it were a genuine pattern in the data. So such model will achieve excellent performance on training data. However, it will struggle when faced with new unseen data, meaning it will struggle on the testing stage, which is the stage that's even more important than training, because that's what determines the final real performance of that model. So the goal is to find the optimal model. So we don't want a model that underfits, and we do not want a model that overfits. We want to find that sweet spot between under and overfitting. So we want to ensure that the model generalizes well to unseen test data without sacrificing performance on the training set. Okay. So this leads us to the bias and variance trade-off discussion. Again, let's define what each one of these mean. So the bias is the error that's introduced by trying to approximate a real-world problem, assuming a simple model. So the model is very simple compared to the real-world problem. On the other hand, the variance is the model's sensitivity to small fluctuations in the training data. So if you have high bias, this often leads to underfitting problem, where the model is too simple, it fails to capture the complexity of the data. If you have a model with high variance, this can result in overfitting. So this is underfitting and this is overfitting, where the model is too responsive to the noise in the training data. So what we want, the optimal model, is low bias, low variance. So this is what we are looking for. So think of an example where we have a well-trained speech recognition model that accurately transcribes diverse accents and speech patterns. It captures the underlying patterns effectively, so it has low bias, and it does generalize well to new data, so it has low variance. So this results in a good, reliable performance. So this is what we're looking for if we could achieve it. Okay, anything beyond that is a problem. If you have low bias, but high variance, here you have created a model that performs exceptionally well on training data, so it has low bias, but it struggles with new and seen test data because it's too sensitive to the variations in the data. So here you have low bias, high variance. This leads again to overfitting and lack of generalization. If you have high bias but low variance, then the model here is too simplistic, right? It's oversimplified because you have high bias, and it does remain consistent across different variations of the data. So you do have low variance. However, you have low overall poor performance of your model. Okay. Again, if you have high bias but high variance, it's still not good. The model is overly simplified and overly responsive to the noise in the data. So it's really bad and poor performing model. Okay. So this is the sweet spot. This is what we're trying to achieve. And so it is really one of the main challenges in machine learning techniques. So you're trying to find that right balance between bias and variance for optimal model performance. So you can see here in this curve the inverse relationship between these two. So when one decreases, the other one increases. So the idea is you're trying to find this sweet spot. You're trying to find the point where the total error of the model is minimized, ensuring good generalization to new and seen test data.